Good afternoon, everyone, or good morning to Daniel. Dan Zucker is here from the East Coast of the US, so it's still morning for him. Thank you for getting up early to speak to us, Dan. We really appreciate it. I think this presentation is going to have a performance flavour to it, and we'll find out if our CICS region is too busy. But as usual, Nick will keep an eagle eye on the chat. You're all on mute, so any questions, if you could just tappy type them, and then we'll interrupt Dan at a convenient point, hopefully, to discuss any of the points that you guys would like highlighted. So without further ado, Dan, please take it away. Cheers.
Sure, thanks, Robert. Right, it's a pleasure to be here, everybody. And I've been in this job for over 30 years, and the same thing, CICS Level 2 support, and I love it. I love working on these problems, especially the performance ones. So I'm sure I've worked with a good number of you over the years. So let's get started and take a look at this one. So yeah, is your CICS region too busy? Mostly it's going to be, is your CICS region's QRTCB too busy? That's a key bottleneck point that we see. It's one of the main causes of performance problems that we see over the years. And so that's what we're going to talk about here. A little bit of monitoring basics and the anatomy of a dispatch and to suspend. QRTCB saturation. There's a new message that helps you see how saturated your QRTCB is. We'll talk about that and a few conclusions and recommendations. All right, so what's the problem? So the organizing problem of this pitch is this. And as you can see, it's a response time problem. Everything was fine, and then for those 3 problem minutes, response time spiked up to about 2.5 seconds for a minute. All right, and this is data that I did in the lab, mimicking a real problem that we worked on earlier this year. The real problem was a group capacity limit problem, just sort of during normal heavy workload. The group capacity limit kicked in at an unusual time during this normal heavy workload, and that caused lots of CPU contention in the LPAR, and that was the cause of the real problem. In my recreate, I just forced it with some soaker jobs. All right, we'll try to move this. Okay. All righty, so a little bit about the QRTCB. There's just one for every CICS region. That's a key thing. You know, it used to be that pretty much everything happened on that one CICS region, and so you got some serialization sort of built in. Only one thing could run at a time. There's only one TCB. And still today, there's application programs that depend on this and need to run on the QR, and some CICS stuff as well needs it. And the bottom point is the key. It's a natural bottleneck point. Almost all transactions do at least some processing on the QR, and so they all have to share it one at a time. It's a natural bottleneck point. And then this is always a slightly confusing thing. All kinds of different monitor products to help us with CICS performance, and they often have a little bit of a different name for the various things. You have to translate all the time. It's usually not a problem, but it's a subtle problem. It can be. And this is true of CICS PA. Down below, this is a CICS PA report, and those are CICS PA names down there. And so instead of using those, though, I'm going to replace them with the sort of the official name from the CICS IBM documentation. So I'm going to use those names. Those are names that you can look up in the IBM documentation and see exactly what they mean. All right, and then some more about this. So this is data all from one CICS region, and that's important for this kind of analysis. You know, I'm asking, is your CICS region, is a particular CICS region too busy? And so all of this monitoring data, which is what is shown on this report, is all from one CICS region. If you look at them as a group of CICS regions, then you can't really tell if a single CICS region's QRTCB is too busy. And then as you can see, each line summarizes 1 minute. It summarizes all the tasks that started in each minute. And most of the columns you see are averages, average numbers, but there's one total one. That's the QR dispatch time total. So that thing is going to total up all the individual QR dispatch time, but for all the tasks that started in that minute, and gives you the total. All right, so in our problem, what's the main cause of the increased response time? And the biggest chunk is this one, QR mod delay. This is time tasks spend waiting for redispatch on the QRTCB, time waiting their turn. You know, only one at a time runs on the QR. This is where tasks spend their time when they're waiting their turn. So that was the biggest chunk here. All right, so there's another spot where you have time spent waiting your turn on the QR, and this is the disp delay. This is waiting for first dispatch, and first dispatch includes any time spent waiting for T-class waits, and it includes any time waiting for a max task, you know, queued for a max task, and it also includes simply time waiting to be dispatched. Okay, so right here, I've tried to sort of subtract out the portion of wait for first dispatch, the portion of disp delay that is for waiting to be dispatched. So I've subtracted out the T-class parts and the max task parts, and made my own column over there on the right, which is that portion of wait for first dispatch that is waiting your turn on the QRTCB. Okay, so that's an additional bit of time waiting to be dispatched on the QRTCB that's different from QR mod delay, which is waiting for redispatch. And here I've tried to add those together. That's the QR mod delay time waiting, plus that portion of wait for first dispatch that's waiting on the QR, and kind of made my own column over there on the far right. And so all of that time is waiting on the QR. And you can see that's almost all of the average response time increase over what was normal. Now, like T-class itself, you can see is a big part of the response time. It's a big chunk, a half a second during that worst minute, but it's, you know, not a primary reason. It's a secondary effect of all the wait for redispatch on the QR. Okay, so one thing I've not included here in these columns is anything like what the tasks might naturally wait on, like file IO or you know, IR wait time, like waiting on the sister transactions in another CICS region. And I did that on purpose to emphasize that often those don't matter. In a case when almost all of the delay is waiting for redispatch, it doesn't matter about these other things. And so I've faked the data a little bit just with this column of FCIO wait time. This is not actually from my recreate. I did have FCIO wait time in my recreate, but that right there is faked out a little bit to make a point. And so you can see during the problem minutes in that FCIO wait time column that looks significant, right? You know, approaching a whole second of time in FCIO wait time. And so if you started there without paying attention to the wait for redispatch stuff, you might say, oh my gosh, file control IO has really ballooned here. That's the problem, let me focus there. And you'd be making a mistake. It's because, you know, this time here in that FCIO wait time column includes the time for waiting for redispatch. And so let's see, I think this next column, yes. So before you focus on a particular suspend type, you need to first look at the wait for redispatch numbers. And if most of the suspend time of a task is wait for redispatch, like we just talked about and saw, then that means that most of the time of any particular suspend type, like FCI await, is also wait for redispatch. All right. So let's move on to sort of the anatomy of a suspend. And here's my little pictures. We're going to sort of build a CICS region and show sort of how it works going on, what's going on inside. So that's my TCB, the QR, and red means it's just sitting there, not executing instructions, doesn't have a processor, just sitting there doing nothing. And then the little green glow, I'm going to say that means it's ready to go. It's just not waiting on anything except for a processor to run on. All right, and then there, that's what it looks like. When it looks like that, that means it's got a processor, it's executing instructions. Okay, so here's the CICS dispatch loop, and this is what happens all day, over and over. And so we're going to start with, it's going to pick a task. We have some transactions perhaps that are just waiting their turn to be dispatched on the QRTCB. So he's going to choose one of those and dispatch it. That means give control of the TCB to that task, and off it goes executing instructions on behalf of that task. So when that's over, when the task gives control back to the CICS dispatcher, then it's going to start over. Are there any dispatchable tasks ready now for the QRTCB? And if not, it does this MVS wait. And there, the QR finally has no task to dispatch, nothing to do, just sits in that MVS wait until something is ready to run, and then it picks one, and that's the loop over and over and over. All right, so the instructions that get executed, well, there's a whole bunch of CICS management modules sitting there that get executed. And there's some system routines that get involved. They get branched to, and other products. The application program, it executes instruction in there. And then over on the right, these are tasks that are all suspended, and those ones over there are waiting on something like file IO or IR link, waiting to hear back from a sister transaction in another CICS region. And this pile, this is the ones that are dispatchable. They either are waiting their first dispatch, or perhaps were waiting on file IO a minute ago, but now are ready to go, and they're just waiting their turn. Remember, one at a time on the QRTCB. And when you get a pile of tasks like that, that's when they're accruing all that wait for redispatch time that we saw earlier. Okay, so we're going to go through a dispatch loop for one of these. So we're going to choose that task 10,001 there, and so right now it's becoming dispatched. We are essentially giving the QRTCB to that task. And I like to say that a task is always either it's suspended, which means it's not hooked up with a TCB, or it's dispatched, which means it has the TCB. All right, so we got to do some housekeeping right here, and before we actually give it control. And so I've got this little chart here. So we're going to say this task started right there. That's smack in the middle of the worst minute, is 17:30:00, and these times I'm giving to this task are kind of going to match with the average of the tasks, the average that we saw earlier in the summary report. All right, and so that first little bit of the task is suspend time. That's waiting for that first dispatch. And so I'm able now, I know when the task was attached, and so here it's being dispatched, and so I can calculate all that suspend time. So that's about a second of suspend time. It's a particular type of suspend time. That's the disp delay. That's the waiting for first dispatch. And then a piece of that was T-class delay. So I put all that in my monitoring fields as part of some housekeeping. And away it goes. So now you can see the TCB is actually executing instructions on behalf of this task, and and the CICS dispatcher is kind of out of the picture. He doesn't have a TCB to run on at the moment. A control is executing instructions on behalf of this task through right here through those CICS management modules, and eventually we get to the application program, and off it goes. And sometimes this happens. Okay, so here, you know, the TCB is red. It lost a processor, and I'm going to read these things. The green glow means that the code did not voluntarily wait on anything. The processor was taken away, and a lot of times that happens if you've used up a time slice. It happens a lot more, of course, when there's lots of CPU contention, lots of other CICS regions or batch jobs or who knows ever, or other TCVs in this CICS region, just lots of contention for the CPU. And the more that is, the more this happens. I'm not sure if I say it on the on the next screen, but you know, this is really, I think I do. I'm going to go. So this QRTCB's world is kind of frozen in place here. You know, time is ticking. That's true. Dispatch time is ticking, but everything is frozen in place. Nothing is happening. All those blue tasks that are dispatchable, they can't run either. This QRTCB is poised to resume executing right where it is when it gets a processor. So the more that happens, the worse it is for these poor CICS tasks that are waiting for their turn. Okay, so now he's on his way again, executing instructions and going about his business. All right, so here we're going to come in, say, doing an exec CICS file control command. So come into a CICS module and off into VSAM, where VSAM will initiate IO. And since VSAM knows it's CICS and so knows not to wait for that IO, doesn't do an MVS wait. But if he did, it would look like this. You know, the no longer executing instructions, everything is frozen. It looks the same as losing a processor. But anyway, so if that ever happens for any reason, it's still the same. It's all dispatch time, and the world is frozen in place. But anyway, that's not the way it works. And so VSAM calls back CICS to wait for the IO to complete. And so what does CICS do? Oh, here I've lost control again. But anyway, so CICS, so we have this ECB that is going to get posted when the IO comes home, when it completes. And CICS doesn't wait on it, doesn't wait the TCB for that IO to complete. Then instead it extends the ECB. So it sets it up so that when it's posted, a post-exit routine will get driven. And so we extend the ECB and then carry on. So control goes back into the dispatch loop. That task that had been using the QRTCB is put over there to wait for that file IO to complete. And now the CICS dispatcher is free to let some other task run while that IO is happening for task 10,001. All right, so a little housekeeping. So we've just finished the first dispatch for this TCB. And so we can update some of these dispatch time fields. So we're going to ask, we do a time used, I believe, to figure out how much CPU was used during that dispatch. So we can know exactly how much CPU is used during that dispatch. And of course, we also know the time that dispatch took. And so in here, I'm going to say that took a millisecond, the whole dispatch. And for a fifth of that, it was executing instructions and using CPU. So that's a pretty bad ratio. And that happens largely on the QRTCB because of CPU contention. Anyway, so we can update those fields. And now we're going to look for another dispatchable task. We're going to choose that one and give control to it, and off we go. Okay, so so here's a key point. So so this task is off using the QRTCB, and now we're going to say that that IO for that prior task came home. It completed. And so a little SRB probably running on a different processor, is going to come to life to post that ECB. And when that happens, so that post exit routine runs, and he's going to move that task to mark it as dispatchable and sort of put it on the dispatchable chain. And CICS remembers that time, so we can calculate the wait for redispatch. So that task, waited a little bit legitimately for that IO, but when it came home, it's now dispatchable, and so we remember that time. Okay, and anyway, the guy that currently has the QR is continuing on with his world. Okay, so I've fast forwarded, and we're going to say that that task gave control up, waited on something, and the CICS dispatcher has chosen task after task after task after task, and eventually we're going to get back to task number 10,001. Okay, so we're going to choose him now and dispatch him. He's been, and the last thing he did, remember, is that file IO. All right, so the housekeeping on him, let's see. So so all that time suspended, we're going to say that's 24 milliseconds. And so we put that time in FCI08. It also is going to we're going to add that bit of suspend time to the suspend time clock. So I'm going to add the 24 milliseconds to the suspend time clock. And then a piece of that file IO time, that 24 milliseconds, is waiting for redispatch. And so I'm going to add that in there to my QR mod delay time column. And the actual length of the IO, the 1 milliseconds, is not directly recorded. You can figure it out, like right now, since there's only been one wait for redispatch. You can see, okay, 24 milliseconds of FCI08 and 23 milliseconds of that is QR mod delay. Once a task is suspended a bunch of times, it kind of gets lost a little bit, and you wouldn't be able to directly tell. But anyway, so this is the housekeeping on that, and that is that piece. Okay, so so that's the cause of all the wait for redispatch is the cause of the problem. So what causes that? And to answer that, we need to focus on that QR dispatch time column. Okay, and so this is my favorite trick, really, with working on these things. The first thing I look at when I have a response time problem is I'm going to get data from one region, and I'm going to have a report that includes total QR dispatch time, and I just want to see, is that QR TCB busy most of the time or not? And so that percentage of time that the QRTCB is busy dispatching tasks is QRTCB saturation. And so for this monitoring data, this is 1 minute intervals, 60-second intervals. And so, for that first line, I have 39 seconds of QR dispatch time divided by 60 seconds of time. And that ratio is the saturation. And so these guys during the normal good minutes, you see, were about 65% saturated. And then when it got bad in that worst minute, you see it's 96%. Okay. Now this is true as well. So monitoring data includes, but often is tasks that finish, and we really don't have any data for like long running tasks that also use the QRTCB. And in fact, the CICS dispatch loop, that uses the QRTCB, and that's not included here either. So it's a little bit of an approximation. Okay, and so it all kind of fits together. When the TCB was most saturated, and in the 1700 minute, that's when there was the most wait for redispatch time. And that's really almost always going to be the case in a typical CICS region with lots of short running tasks. When you get close, when you get into the 90s of QRTCV saturation, you're going to have a response time spike, with mostly caused by wait for redispatch. All right. So so what caused the total QR dispatch time to spike up to 96%? So one thing that could cause it is simply more tasks during that minute. And so I'd look at that, and that's not the case here. In fact, there's less tasks in the problem minute. So it's not like there was suddenly more work in terms of more transactions. So it probably is that on average, each transaction then must be using more QR dispatch time. And that's indeed the case here, a lot more. You see like 400 microseconds during the good minutes, and then during the bad minutes, it spikes up to 800 and 2000 microseconds. And so that's why saturation went close to 100%. It's because for some reason, tasks started using more time on the QRTCB. Okay, so now we're gonna, why is that? Well, in our case, it's because of lots more CPU contention during that bad minute, and it causes the QRTCV to lose a processor much more often. And the way to sort of measure that and gauge that is with this CPU to dispatch ratio. And like if you look at that QR CPU T column, the highlighted column on the left, so that's the average CPU these tasks use, and you can see that didn't really go up or anything. So it's the same amount of CPU, but it took longer. And that's the problem here, is the same number of instructions, the same path length of stuff. It just simply takes longer because of losing the processor. And so there I've put that QR CPU dispatch ratio over there, highlighted now on the right. And it kind of fits. You can see that CPU dispatch ratio, when it tanks, when it gets really, really low, that means tasks are spending more and more time on the QRTCB, and that's when saturation grows. All right, so let's talk about statistics. So there's a couple of ways to use statistics to keep track of this, and it's really the best way for saturation, because it does include long-running tasks and the CICS dispatch loop. But the statistics are often in big intervals, like maybe 3 hours, or sometimes 24 hours, or sometimes an hour. And so of course a problem minute like we've been looking at would get lost in the statistics from, say, a 3-hour interval or even an hour interval. And it'd be so much better to when you have a problem, to be able to see what is saturation during just that minute, say. But anyway, I find a lot of shops just have the end of day statistics, every 24 hours. But anyway, let's take a look at a little example. This is a STUP report that is, you have to sort of know how much time is this STUP report reporting on. And this is a 15-minute interval kind of a thing. And you can kind of work it out just from this. The QRTCB is either waiting or it's dispatched. And so you can see that wait time and dispatch time add up to the 15 minutes. And the STUP does report that interval over there. I think it's covered up on my thing, but we throw that CPU to dispatch ratio and give that to you over there, but we don't put a number on the saturation. you kind of have to come up with that number yourself. So, which is the dispatch time, 4 minutes and 39 seconds, divided by the interval, which is 15 minutes. So this one, it's not all that busy over the course of that 15 minutes. 5 minutes of dispatch time will say to 15 minutes of time. All right, the stat transaction is another way, and you can run that and produce a little report like this. And that one also computes that CPU to dispatch ratio. That's the number we've heard about for years and years and years, which is a measure of how, are you getting the CPU when you want it? But we don't make it easy to figure out the saturation ratio. How busy is the QRTCB over an interval of time? And so here you take that somewhere in that stat report, it tells us this covers 56 seconds since the last reset. And so here you would take those 32 seconds of dispatch time and divide it by the 56, and you could calculate your own saturation ratio there. So we make you work for that number. All right, so there's this new message at CICS 5.6 that gives it to you. And so you can have it set as low as every minute. It'll put out a message saying what was the saturation ratio over that minute and what was the CPU dispatch ratio over that minute. Or it can be up to 59 minutes, or you can turn it off. And so this is what it looks like, and this is the actual numbers from my recreate. And so you can see during that worst minute, it really did get up to 100% saturation. And so just from that, you can just imagine, pretty much know that during that minute, there's a pile of those blue tasks waiting for redispatch, and so much of their response time is that. You can kind of know that just from that message. And then so that's the last of these two ratios. The first one is the CPU dispatch ratio, and you can see how it kind of fits. When the CPU dispatch ratio tanks 23% there, tasks are going to be using the QRTCB longer, which makes it more prone to saturation. And so you can see it, and you can see it much more easily with this message. And so with this message, you can if let's say you had a feel for, okay, on an hourly basis, my QRTCB is like 50% busy, perhaps from looking at stats. So here you can get a much granular view of what the saturation is and that CPU dispatch ratio is. All right, conclusions and recommendations. So not all regions are the same. So this CPU to dispatch ratio. So we've heard over the years, 90% in the 90s is good, in 80s is okay, and so so anyway, not all regions are the same. You kind of need to figure out what's normal for your region. Heavy use of RLS by quasi-rent programs can affect this, and HPO equals yes for like TORs with lots of VTAM activity. Need to kind of get used to what's normal, and then know that it's going to fluctuate. There's bad days, there's heavy CPU contention. You might hit your the way that problem was, the max, forget the the cap limit was reached. Things happen, and and so your QR CPU dispatch ratio gets worse sometimes, some days, some hours, some minutes. And when it does, then you know your tasks are using more QRTCB time. So it's helpful to know kind of what's normal, and then you can and then you can recognize it when it goes bad, using that message really is a easier way to do that now. And then but the really key thing is the saturation, the ratio on the right, the dispatch time to interval time, because when that gets too high, you're going to have a response time problem. And let's see. So what's too high? And so I'm making these up, but I say 0 to 50%. The QRTCB, if it's in that range, then that's good. When it's in that range, you have room to absorb a bad day. Say a doubling of that. Much more CPU contention. You're going to use more QRTCB time. You're going to be, if you were 50% saturated normally, you're going to go up, but you have some room to withstand that. But if your normal during a busy time is above 50%, 50 to 70% or higher, then you're prone to problems. In my Recreate, my normal saturation was in the 60s. And so I ran my soaker jobs, and so that caused me to get up into the 90s, and I have response time problems. If your baseline during a busy morning is below 50%, you have more room to withstand things like increased CPU contention. Alrighty. So a few little details about this message. So that APAR there, that PTF, that one has a few changes to the messages and fixes to it. Like in the beginning, you couldn't turn it off. Now you can turn it off. By default, it'll come out every 5 minutes. And then another thing is we don't issue the message when QRTCB saturation is less than 5%. This is to keep it from like a test region, and overnight it's not doing anything. We won't keep putting out that message when nothing's happening on the QRTCB. All right, and then from a service perspective, kind of my perspective, it's a great data point for working on problems like performance problems like the one we went through, or even hangs. A little, I've got a hang, and yet, oh look, I was able to put out that message at that time. It's a data point that helps with debugging. And from a CICS systems programmer's perspective, it makes a much an easy way to track QRTCB saturation. You guys are, I think, you're kind of blind. You have stats, but as you saw, you have to work for it a little bit for this QRTCB saturation number. And the stats are over a big period of time. With this message, let's say down to a minute or 5 minutes, you can see during a busy time, what is your QRTCB saturation? Is it, some shops have hardly anything on the QRTCB. It's open TCBs and Java, and this is just not an issue. A region like that is not prone to this QRTCB bottleneck. But other regions, it's still the norm. Most everything happens on the QRTCB, and if it's too saturated, you're prone to response time spikes in periods of CPU contention. And so you can easily see that now with this message. So I think it would be useful for a CICS systems programmer as well. All right, I think that might be it. So Nick didn't jump in with any messages. I'm gonna check out this chat right quick.
Hey Dan, no, there's been no questions posted in the chat yet, but that doesn't mean that someone might not quickly come in now.
Sounds good. Anybody have a question about any of this?
So are these common queries that come into level 2, Dan?
Yes, definitely. Sort of an unexplained response time spike. You know, we see, yeah, you know, every week.
Right.
And
it's a fascinating insight, Dan. I don't really have a question so much, but I've been around CICS for a while, and QRTCB has always been, you know, a concern, and it's possibly less of a concern now. I mean, what I used to see years ago was just CICS region running out of CPU, which was really easy to see. QR only used one engine, so you had to be careful when you were looking at your workload if you couldn't split out to other regions. But nowadays it doesn't seem so easy to me to work out what's going on. There are still some bottlenecks that CICS creates itself, in so much there's an awful lot of tasks that have to start on the QRTCB, even if only momentarily, and then get off and do something else. So this is a fascinating insight to me of what you guys have to look at when you get these dumps and traces and reports about what's going on at our end. And I really enjoyed the explanation around the dispatcher and when things are waiting for dispatch, which that's always intrigued me. But it was interesting to see your perspective on it. And I think we've got some questions now, Nick.
Yeah, we have. Thanks, Rob. So Dan, you mentioned a cap. Do you mean the Tran class or MXT?
I believe that's the very beginning of the thing. The actual problem I said was caused by the capacity group limit cap, I believe it was. And no, that's nothing to do with CICS. That's you know, one of these, like it's a ZOS systems programmers kind of a thing. You have a rolling 4-hour average of CPU, and when that rolling 4-hour average exceeds something, then WLM or ZOS or somebody will say, all right, that's enough. You can't exceed the CPU anymore that you have been over the last 4 hours. And so that puts and so when that kicks in, it makes things, you know, not get the CPU that they want. So it's not a CICS cap at all I was talking about. If I guessed right on the, let me go back to the beginning.
So Rich, was that the question you were asking?
Oh, I can unmute now. Yes, that was it. Thank you.
That's it. You're cool with that, are you?
Yes.
I'll ask Sheldon to unmute. He has a question about RMI delay.
Hi, I found this very interesting, and what I find when I think that I'm being starved, CPU starved, is that the CICS monitor or CICS PA shows very high RMI delay times, and I assume that's in DB2. And then I go to my DB2 monitor, and it shows that there's no delay in. It shows an application delay. Could that also be because of CPU?
Yeah, maybe, but for sure a much better sort of indicator of CPU contention than something like RMI delay is this QR CPU to QR dispatch ratio. You know, the QRTCB, this is pretty much always true, it's supposed to be executing instructions. It doesn't wait on things. It's just executing instructions. And so when it gets all CPU it needs, then it can just execute instructions solidly, and your QR CPU time is going to be the same as QR dispatch time. Let me go to one of these.
Yeah,
oh well.
I think
Right.
this is an interesting example, Dan, because with your ZOS workload management or capacity situation, you've got a situation here in this report where CICS can't get CPU, but probably DB2 can. And one of the most common scenarios I think we see is when we have a bit of a slowdown, all the started tasks on an LPAR perhaps are impacted. And so you would see a lot of RMI waits because we're waiting on DB2 because DB2 is waiting for CPU.
Yes.
So I see that sometimes. Yeah,
that's definitely true. So so the best place is this ratio of QR CPU to dispatch ratio. Okay, but absolutely true that in your shop, when you have CPU contention, it makes RMI time to be high. That could be true, but using RMI time, high RMI time as an indicator of lack of CPU is, I would say that's not a good way.
Yeah.
But I also wanted to say, but true. So if the QR is suffering, if the QR CPU to dispatch ratio is bad, then the other TCBs are going to be as well. You know, your work over in DB2, it's going to be suffering as well. But I want to make this point too. So the work over in DB2 happens on an L8 TCB, not the QR, and you can kind of get the ratio like the L8 CPU to the Key 8 dispatch time, and the reason that's not a good ratio to pay attention to is that over in DB2 you could wait the TCB like on a lock or something. And so having a bad ratio looking at this L8 TCB doesn't necessarily mean CPU contention. A bad ratio with the QR mostly does mean a problem with CPU contention. But anyway, so you say that, so you have RMI time, and then you go look at DB2 stuff, and they say it's like application time. Yeah, that happens some, but yeah, I don't associate it with CPU contention. Here, tell me again. So high RMI time, high RMI DB2 time, and then what do you look at then in DB2?
I look at Omega-Mon DB2, and I would expect it to be CPU in DB2. And DB2 says, no, I'm not using CPU. I'm not waiting for CPU. I'm waiting for the application. It's like CICS is waiting for DB2 and DB2 is waiting for CICS. But I do suspect, and I see that other applications and other CICS regions are running fine.
Yes. So one thing, the work in DB2 in processing SQL calls from a CICS transaction happens on the CICS TCBs. There's probably some exceptions to that with parallelism and things, but in general, it happens on the requesting TCB, and so I'm a little unclear on the DB2.
L8, the L8 TCB, right?
Yes. So DB2 monitor saying we're not starved for CPU. Is it talking about because this CPU is charged to CICS, and is it talking about just internal DB2 processes? DB2 doesn't use a lot of CPU as an address space. I think is true.
Yes, I'm talking about Omega-Mon CICS and Omega-Mon DB2.
Okay.
Now, if I go if I've got a transaction in CICS and I see the RMI delay time very high, 1 second, I would go to DB2 and expect on the same thread to see 1 second of CPU time on that thread, because the Omega-Mon DB2 shows the CPU of each thread. But it doesn't show 1 second of CPU, it shows 1 second of wait.
Yeah, but it could be a lock, couldn't it?
Yes,
It
is it
doesn't necessarily be CPU?
No, there's no lock. That's the funny thing. That's why I still suspect that my CICS is lacking CPU.
I would take a look at that QR CPU dispatch ratio.
Yeah,
And,
that's what I'm gonna do.
Okay, and then if you're at 5.6 and that message, you know, you could. It's an easy way to check that ratio. And does the problem sort of last for a minute or so, and then goes away? For
a few seconds.
Oh, okay. Yeah, even that message wouldn't really help for a few seconds, kind of a thing. So yeah, that's a little bit of a puzzle. That's kind of hard to work out here.
Okay, thanks.
You're welcome.
Hey, Dan, thank you for that. Wendy Wilson has asked, you talk of these for TS 5.6, we're at 5.4. Are there any of them applicable to 5.4? I'll unmute Wendy because I'm not absolutely sure when she says these, what she means by these. But there may be some functionality or changes that we made between 5.4 and 5.6. But broadly, I think most of what you've been showing has been in CICS for years.
Oh, well, that's good then. It's just that I'm new coming into looking at this sort of thing in CICS, so that was just my question. Are these all features available in 5.6, or are they all available to 5.4?
Right. So the monitoring data and statistics like DFH stub that we've talked about here, it's all at 5.4 and for years and years and years. The only thing that's just at 5.6 is that message, that DFH DSO102 message that externalizes some of these key indicators. That's new at 5.6. So you can still analyze QR CPU dispatch ratio with monitoring data or with statistics that you from running DFH stop. You can still do all that, but just the convenience of those ratios being externalized in that message, that you can only get at 5.6.
Thanks, Dan. We've got one last one. Well, I say last one. At the moment, it's the last one from Jiva. What is other wait time?
Yes.
In suspended wait time, is it something not captured or something which is uncategorized?
Yes. Right. So there's a whole bunch of things you can suspend on in CICS, and there's a bucket, a monitoring field for most of them, but not all of them. Years ago, allocate wait time was one of those. And so if you spent a second waiting an allocate wait, there was no particular bucket for it. And so it was included in suspend time, but nothing else. And we fixed that problem. That was a pretty common wait type. And so years ago, that got included, a special bucket just for allocate wait time. There are some, we do not have a bucket for every type of suspend. And so I'm pretty sure that this other wait time is things that don't have any particular bucket other than suspend time. So I think you'd call that uncategorized. It is captured. All suspends are included in suspend time. A task, you're either dispatched or you're suspended. So a task dispatch time plus a task suspend time will equal the task's response time, start time minus stop time.
So are we kind of saying, Dan, if it's other, we just can't tell, but is there like a list of things that it could be that you guys have somewhere in a cupboard, or is it just time to scratch your head if you get other wait time?
Right. Yeah, I'm sure we can figure it out for sure. If you have a consistent problem, or with that, I'm sure we can figure it out. But I think there is There probably is a list of suspend types that don't have their own category. You know, if it's something pretty common, we would probably
Okay.
include a
I think we
category
might
for
have
it.
an example of that somewhere, but it would be a good one to share, I think.
Sure. Not at my fingertips.
No,
Is
we've
it-
got one. We've got one. We can send it to you. Don't worry.
Okay. All right.
Hey,
But yeah,
Dan.
one other thing about this other wait time, sometimes data is excluded with an MCT, just kind of to make them smaller. So let's exclude the FEPI weights and this and that. So CICS-PA probably, if it's working with data where a lot of these buckets, a lot of these categories have been excluded, it'd probably lump those in an other wait time category, even though they're excluded on purpose with an MCT versus one that there's just not a category for that particular type of wait time. So I think that can happen too. If you exclude fields with an MCT, that can make there be other wait time. So that's possible too. All right, so were you saying something, Nick?
I was just going to say we're coming up to the hour. There are no more questions in the chat at the moment. You might want to just put your screen onto the feedback page, because I think a lot of people have got an awful lot of information and insight. I think a real insight. It's not just been numbers. It's been actual useful information and insight. So hopefully they'll value your session highly, and we can knock Mark Nelson off the perch and get you a best session or something. But
Yeah. Okay.
I'll hand over to Rob for the final wrap.
Yeah, I think, Dan, it's been a fascinating insight into how you look at these figures and how you deal with problem resolution. I've been enthralled on this one more than I have with any session so far in the last 2 weeks. So on behalf of CICS in the UK, thank you very much for the presentation. And we really appreciate it. Folks, as you can see, it's session 7 AV. There are prizes to be won if you fill this form in as well. So please, I encourage you to fill the form in to the best of your abilities. And continuing our performance theme this afternoon here in the UK and in the morning in America, we've got another American chum, Ezrail's coming along in half an hour to do some presentations, I think, related around CICS-PA and performance. So look forward to seeing you then. Thank you again, Dan. Really enjoyed it.
Yeah,
You're
cheers,
welcome.
mate.
Thanks, everybody. Bye-bye.
Bye. Cheers, everyone.
Hey, Rob, I may be cutting it a bit fine for the next meeting, but I will be there. I've just got to jump onto a Nordic call now.
No worries at all. See you then. Cheers.
See ya.
Bye-bye.
Bye-bye.